the second type of structural member that we'll consider in this course is the Bernoulli-Euler beam. Euler beam element, in a sense of structural element. Okay? And again, we'll proceed using the differential equation approach. Equation approach, right? So we are on page 1-8 of the reader. Okay. So what the beam does, right? It takes vertical loads, okay, or transverse, loads, and it responds in bending. In so-called bending. Okay. So let's make this a bit more mathematically detailed. Again, I'm sure you covered a lot of that material in 310, but let me just summarize it for everyone's benefit, and it will be instrumental in this class. Okay. So the easiest thing to see here, right, is you start with something that's straight. Okay. And that beam will have a median axis. Okay, remember, this is y. All right. Then if you look at the cross section and if you perform the integral over the cross section, okay, and then you put the density here, okay. In fact, maybe we don't need there's no need for density, okay. Assume density is constant, right? And you just write y minus y0, okay, dA, okay. And you equate that to 0, okay. This gives a definition of y0, which is a coordinate of the beam median axis. Okay. And so if you can imagine, right, if you have something of rectangular cross section like this, right, the median axis will just respect this line of symmetry, right? I mean, if you have a beam cross section that looks like this, right, then you know, this guy will shift accordingly, right, toward the larger edge. Okay. And so let's go back to the side figure, right? This is your beam. We incorporate this guy, right? Put it in the x, and now we need the y coordinate system as well. Okay. And supposedly, right, this is the middle axis. Right? Supposedly you apply some vertical loads. Okay. And then the beam undergoes a deformation. Okay. Right? It looks something like this. Okay. It develops a local curvature. Right? And here I'm going to plot the location of the middle axis. Okay. So now there is some constraint on the deformation, right? So if you start by drawing a line that's perpendicular to the middle axis like this, and you put a right angle here, 90 degrees. This is a point A, this is a point B, okay? Supposedly A maps to here, B maps to there, right? And they can be connected by a straight line here. Okay? That straight line will always be perpendicular to the middle axis in the deformed configuration. Okay. So in other words, beam cross sections remain planar and normal to the beam axis. In the deformed configuration. Okay. And so what happens is you apply these transverse loads, right? Locally, the beam will develop some curvature. Okay, so something that's straight, okay, will develop, a region with a given curvature radius. Okay, and then what's not allowed are deformations of the form where the cross section AB, right, starts forming angles, okay, with respect to the middle axis. What these do, these give rise to so-called transverse shearing deformations, okay. But in the Euler-Bernoulli beam theory, these transverse shearing deformations are precluded, okay. And so implication is no transverse shearing deformations are allowed in the Bernoulli-Euler theory. And this assumption is okay for sufficiently thin beams, okay, or slender. Okay, if they become sort of more three-dimensional, they get a little bit thick, compared to the length, then in order to get a better theory, you need to start accounting for the transverse shear deformations. But for our purposes, we don't need it. Okay. All right. So just like for the truss case, let's look at the free body diagram, FBD. Right. I'm sure you've seen a lot of those, and you're hoping you'd never hear FBD again. But here we go. Okay. And here again, as before, right, we're considering a section of the beam. Okay, of size dx. This coordinate is x. This coordinate is x plus dx. Okay, dx is small. This is the median axis. Right? I'm going to denote the transverse load, right, by W. Okay, now it's WY, right? Not to confuse with WX, right? But it's still a function of x, right? So it can change as you traverse from the left side to the right side of the beam, okay? Right, and so for the purposes of this structural member, right, the only action that we can develop, okay, are transverse forces and bending moments, right? So let's designate xy axes here. This is again going to be our point A, around which we're going to be seeking equilibrium, okay? And this guy could be subjected to a shearing force, right? Distributed shearing force. I'm going to call it V, okay? And the moment that I'm calling M, okay? On the other side, V plus delta V, okay? In the opposite direction, and the moment M plus dm, like this, okay? So V is shear force, or transverse force, okay, and M is the bending moment, okay. So and again, this is probably something you've seen in 310, you sort of adopt certain sign convention, okay? So if we're looking at the infinitesimal piece of the beam, all right, situation like this gives positive shear, okay, we call, right? And situation like this gives negative shear, okay? As far as bending moments are concerned, right, we're dealing again with two dimensions here, right? So moment that creates a convex curve, right? So this is a positive moment, and then moment that creates concavity is a negative moment. Okay, so this is sort of the nomenclature that we'll be using going forward. Okay, and so now we need to look at equilibrium again, static equilibrium, but we need to look at the equilibrium of forces and moments. And we're going to look at those around, you need to pick a point, okay, around point A. Okay? All right. So let's see. Let's start with the forces first. Sum of F, but specifically now in the y direction, right? There's no action in the x direction, so we'll skip it. And if we look at the sum of forces, again, looking at the figure, right, we have V oriented in the positive direction, right, minus V plus dV, okay, and then plus, right, we're going to take our distributed force Wy, evaluate at x, right, point A, and multiply by the length of the interval, dx, right? So W is the vertical force density per unit length, right? The piece of the beam is dx long, so the total force is that, right? These are the only forces acting in the vertical direction. The end result is 0. Okay? Likewise, if we look at the moments around point A, okay? And here, remember, moment going like this, right, clockwise, is negative, counterclockwise is positive, okay? So with that in mind, right, the first one is clockwise, so minus m plus m plus dm, okay? And then, if you look closely at the figure, you also see the action of Wy, okay, which will create a moment around A. So what will that moment be, okay? So think about Wy, right, creating sort of a effective force, right? Let's call it Fy, okay? And then Fy would just be a product of Wy times dx, okay? This will be our Fy, okay? And then that force will create a moment, right? Again, because this is infinitesimal piece, we assume Wy is constant, right? And in that case, the effective moment arm, okay, will be this, which is dx over 2, right? So Fy is that, right? And then the corresponding moment would be Wy, right? Will be Fy times dx over 2, okay? And so that's exactly what we're going to add here, right? Plus, right, x counterclockwise, Wy, right, times dx, gives me the force, and times dx over 2, okay, gives me the effective moment, right? And that equation equals to 0. Okay? And so we do have two equilibrium statements, one for the forces, one for the moments, and I'm going to use them to boil things down to the problem differential equation. Okay? So first, let's focus on Fy, okay? And we can see a very natural cancellation of V. So this V will go cancel with this one, okay? As a next step, again, we can just go ahead and divide through by dx. Okay? Once we do that, the first relationship emerges. dv dx equals w y of x. Okay, so rate of change, right? Spatial rate of change, or the derivative of the vertical force with respect to x, okay, is equilibrated by the distributed load wy. This is the first equation. Okay. Now let's go to the moment equation. Okay. Looking at the, and I think there's something we forgot, and that something is an additional force, right? An additional moment. And that moment is generated by this force, v plus dv, right, times dx. So let me erase that 0 here, right? Then I'm going to subtract v plus dv, right, times dx, and then set the end result to 0. Okay? All right. So first we cancel what we can, so m's go away, right? Next thing, I'm going to go and divide through by dx. Okay, this is gone. So we get dm dx here, and one of those dx's is gone. Okay. So then what do I have left? I have dm dx. Okay. Right. Plus wy dx over 2 minus v okay, and minus dv dx, right? Or sorry, that dx goes away, minus dv. Okay. Then I'm going to take the limit as dx goes to 0. Okay. This term survives, right? So dm dx will go to a derivative. Okay. V is v, it's independent of dx, so it's going to have a finite number. Okay, as dx goes to 0, this goes to 0, right? And as dx goes to 0, the right side approaches the left side, and the change in the vertical force also goes to 0. Okay? And so this guy gives me the second equation, where dm dx equals to v. Okay, I have a coupled system. Okay, so the rate of change of v, dv dx, is a distributed load, right? And then the rate of change of the moment is the vertical force itself. Okay. So then what I can do is use this expression, right, and this expression, differentiate again, right? I get this, d squared, this becomes d dx, okay? And then I look above, and I replace this with wy of x, okay? And arrive at one governing differential equation. D squared m dx squared equals wy of x, okay? So second derivative of the moment is balanced out by the distributed vertical force, okay? So this is similar, right, to the truss element, where first derivative of n, remember axial force, was wx. Here, second derivative of m equals wy. Okay? So at this point, again, I could use the same arguments. It's not practical to work with m as an unknown. For example, how do you specify boundary conditions? Yeah. So then you need to invoke some combination of constitutive modeling, right? And compatibility, as we did for the case of truss, okay? And so constitutive modeling, again, we assume linear elastic solid, okay? And with some effort, as you've seen in 310, right, what you can find is m of x, right, the moment at every point, is related to something called the curvature, kappa of x, okay, through the parameters e, right, Young's modulus comes back again, and I, okay, as a function of x. So I of x is the area moment. And the area moment can be computed as integral over a, right, for a given location x, y minus y0 squared dA, okay, where y0 is the location of medial axis. Okay. So the point is, it's a purely geometric parameter. And can be computed for any cross section. Okay, so you're not only limited by beams with rectangular cross sections or cross sections some symmetry, you can do whatever you like. Okay, so basically a linear elastic solid, remember, right? This was sigma equals E epsilon, okay? But now in some sort of tensorial form, okay? After some derivation, you can arrive at this, okay? So M is the moment, I is the area moment or moment of inertia. Okay, and then K sub x is curvature. And so this is where compatibility comes. Okay. Where curvature, kappa of x, is modeled as a second derivative of v with respect to x squared, where v of x is vertical displacement of the medial axis. Okay? So I urge you to go into your calculus book, okay, and look at expressions for curvature. Okay, and what you're going to find is you're going to get a second derivative, right, and then there'll be something in the denominator, which is 1 plus a little correction, okay, and that correction would make things nonlinear, meaning the curvature would then be a nonlinear function of v, and this is something that we're trying to avoid in linear structural analysis, right? But the good news is that that correction becomes less and less important, right, as the radius of curvature becomes bigger and bigger, meaning as your structural member becomes more and more flat, okay? And so this is a perfectly fine definition of curvature for our purposes, right? And this is also a perfectly fine definition of constitutive modeling, right? So what that says is that if you go, right, and you apply some moment locally, okay, that moment will result in local bending, right? Meaning the material that was straight will bend locally into a circle with curvature kappa, okay? And then E and I act sort of as a proportionality factor, right? The product of the Young's modulus and moment of inertia is the proportionality factor between the curvature and the moment, okay? Just like Young's modulus would be a proportionality factor between stress and strain, okay? Okay. And so at that stage, right, we can put everything together. And we arrive at the following expression. ddx squared, second derivative, okay? Remember, of the moment equals to wy, but the moment itself, right, m, is proportional to the second derivative of the vertical displacement. Okay? So I get E, I, possibly a function of x, d squared v, dx squared equals to wy of x. Okay, so still, right, still a differential equation of a single variable, right? So all the derivatives are with respect to x, but the unknown is a displacement that's perpendicular to x. Okay, so this is important to understand. V of x is a vertical displacement, okay, as a function of axial coordinate, okay? And so now, when we're going to put things together in the future, right, you can see that the truss action and the beam action can be put together, okay, into a beam column element, okay, where the axial component of the displacement, right, will be governed by the second order differential equation of a truss, and the vertical component of the displacement will be governed by now fourth order differential equation of the Euler-Bernoulli beam. Okay. All right, and so as before, right, if E and I are constant, we get the so-called prismatic beam, okay? And in that case, the differential equation looks like this. EI, d to the fourth v, dx to the fourth equals wy, the function of x. Okay. Yeah. And so again, rather than working with moments, we work with vertical displacements, okay? And the equation becomes a fourth order equation, differential equation on the vertical displacements, but that is what governs sort of the beam bending action. Okay? So, solutions. How to obtain solutions to equations like this? Well, abstractly, nothing is different, right? So v of x, we're still decomposing into the homogeneous h of x plus vp of x, right? Homogeneous and particular components, with the same definition of the homogeneous and particular components as before, right? So homogeneous satisfy the differential equation with a zero right-hand side and without regard to boundary conditions, right? VP satisfies the equation, you just need to get one expression for a particular right-hand side. And then you put things together and apply boundary conditions. Okay, let's go through an example. This is a classic. Okay, it's a cantilever Bernoulli-Euler beam. Okay, so here we're going to take a wall. Okay, we're going to take a beam, put it into a wall. Okay, like this. And then we're going to put a distributed load on it. We're going to assume it's constant and it's pointing downward. So Wy of x, all right, so if this is the x axis and this is the y axis, becomes minus W, okay, just like that. Okay, constant and pointing in the negative direction. Okay. So we assume that the beam has properties EI, that E is given from laboratory tests, and I depends on what you choose to be the cross-section, right? But we're going to keep things abstract. Okay. This guy has length L, and upon the application of this load, right, the beam undergoes deformation, right? Deforms into something that looks like this. Right. Whoops, erased too much. Right. So something like that, and then something like this, right? And so this deformation is going to be our V of x. Okay. Good. All right, so the differential equation is EI d to the fourth V dx to the fourth equals to Wy of x, in our case, just equals minus W. Okay, next, boundary conditions. Okay. So recall in the case of a truss, we had two possibilities. Right? You go to each endpoint and you prescribe either a displacement, right, kinematic, or force boundary conditions. And the force boundary conditions translate to the conditions on the strains, right, to the derivatives of the displacements in our case. Okay. In this case, you have more options. Okay. It's a fourth order differential equation. Right. So in principle, you can set boundary conditions up to the third derivative. Okay. And so you still have two varieties, kinematic and force. Okay? But in this case, the kinematic boundary conditions are the conditions on V and dV dx, okay? And the conditions on force are the conditions on the moment, okay? Which is equivalent to the conditions on dV d square V, right? dx squared, and the vertical force, which is equivalent to d cubed V, dx cubed. Okay? Good. Right. Now, what else do you know? So you set two boundary conditions, two BCs at each boundary point. Okay? And the way you proceed is as follows, right? If you know the displacement, okay, then you set it. Okay? If you've set the displacement, that you know you cannot set vertical force boundary conditions. Okay? Those two are incompatible. Okay? Either one or the other. Okay? Then you set dV dx. You can do that. Okay? And in that case, you cannot set the moment. Okay? If you don't know that, then you set the moment. Okay? You can do that. right? But then you cannot set dv dx, right? Because they are exclusive. And then if you set v, you cannot set the displacement itself. Okay? And so you go down the list, okay? If you know this, you set it. If you don't know, you move on, you try to set this, okay? As soon as you've accumulated 2, you're done, and then you have to go to the next point. Okay, this is how this works. Okay, so let's apply things to our cantilever beam, right? And let's focus on x equals to 0. Okay. So this point, right, this whole cross section, in fact, cannot move up or down. Okay, so things are easy. V of 0 equals to 0, right? And also because the whole cross section is cantilevered, right? Either which way you want to bend it, the mid surface will always come in with a 0 slope. Okay. What this means is dv dx at 0 equals to 0. Okay. So for that setup, you're setting the displacement and you're setting the derivative or the slope. Okay. Displacement and slope boundary conditions, right? You have 2 conditions, you're done. You can't set anything anymore, okay? Which implies that you don't know what your vertical force is going to be and what your moment is going to be, and just by looking at the problem, it's clearly true. You don't know, okay, without solving the problem. So x to 0, x at x0 just happens to be a purely kinematic point, right? All the boundary conditions are kinematic boundary conditions. Okay, let's go to L. All right, and you agree with me, right? As you change W, right, the beam will bend more or bend less. So you don't know the vertical displacement, okay? Right? You're also not constrained to a particular slope, okay? So in fact, the more you bend, the bigger slope is going to be. So you cannot set V, you cannot set dV dx, okay? So the only thing that remain are the moments, right? And the vertical forces that you have to set, okay, equals to. So for this case, right, you go to the edge, we're not applying any moments or any forces, right? We're only applying the distributed load, which is vertical, and we're letting the beam deform freely, okay? So as a result, both of those need to be 0, okay? Good. Okay, so let's generate the solution now, right? Let's start with homogeneous. Okay, and the homogeneous solution gives us the following, right? D to the 4th, VH, dx to the 4th equals to 0. Okay, so we need to come up with a function, possibly with some unknown coefficients, right, that satisfies that equation precisely, okay? And now, we can do the formal, can come up with a characteristic polynomial, which is not going to be so interesting, right? Another way to reason is as follows. Okay, supposedly V is constant, okay? Derivative of a constant is 0, fourth derivative of a constant is 0. So clearly anything that has that is a constant, call it C1, okay, will satisfy that equation. Okay? Supposedly V is a linear function. First derivative is constant, second derivative is 0 already, right? So plus anything that looks like this, C2x, that'll work, right? Okay, what about quadratic? First derivative linear, second derivative constant, third derivative 0. So quadratic works as well. Okay? And finally cubic. Right? First derivative is quadratic, second derivative linear, third derivative constant, fourth derivative 0. Plus C4. X cubed. So anything of that form, right, any cubic polynomial will solve this equation here, okay? And so this becomes our homogeneous solution, okay? Now our particular solution, satisfies the following equation. EI, right? D to the fourth V dx to the fourth equals to minus W. Okay? So then I'm taking a function, taking its fourth derivative, multiplying that by EI, and I'm getting a constant value. So clearly, V has to behave as x to the fourth. Okay? We just need to come up with the right coefficient. And the right coefficient comes out to be minus W, right, the applied load, over 24 EI times x to the fourth. Okay? So this is our particular solution here. So you can check. Take this, substitute back, and you'll see that that's exactly it. So the total solution is going to be comprised of VH plus V particular. Okay. Okay. So what's the next step, right? We need to compute C1, C2, C3, C4, given boundary conditions above. Okay. Let's look at those, right? We have 1, 2, 3, and 4 boundary condition statements, and we have 4 coefficients. Okay, so again, everything checks out. Okay, so I'll let you follow the notes. Okay, take a look at page 114 for finding the constants. Okay. But the end result becomes V of x, deflected shape, right? Deflection of the neutral or a median axis is 1 over EI, okay, times minus WL squared over 4 x squared plus WL over 6 x cubed minus W over 24 x to the fourth, okay, and this holds for x less than or equal to L greater than or equal to 0. Okay, so everything is written in terms of the problem data. Okay, so that's your displacement shape. Okay, it's quartic. All right, so in particular, if we take V, evaluate it at x equals to L, we get minus WL to the fourth, okay, over 8 EI. So that's interesting, right? If I double the length of the bar, okay, under the same vertical load density, okay, it will displace 4 times more at the tip. Okay, interesting. Okay, again, as I mentioned before, calculating displacements is not the most important thing in structural mechanics. Okay. What's more important is to understand the distribution of moments and the distribution of vertical forces. Okay, because for a given cross-section, a structure can only take so much force or so much moment. Right? If the force exceeds the structure's ability to take it, the structure breaks. Okay? So that's the most important part. And so the moment can be obtained, again, from our combination of compatibility and constitution. EI d squared V dx squared. Okay? And then you can just take the derivative of the expression that I derived before. Okay, and obtain the following. Minus WL squared over 2 plus WLX minus W over 2 x squared. Okay. So if you plot it from 0 to L, okay, it starts out here as minus WL squared over 2, okay, as you would expect, right? Remember, constant load, right? It's the same as putting a force in the middle of the bar, right? And so the total force is going to be W times L, and then the moment arm is L over 2, so you get this. Right? So at the end of the day, things check out. And if you evaluate at L, you get a 0, right? And the solution comes in like this. Okay. Okay. Very good. Right. Also, the moment, right, is such that it's making the bar concave. So it's negative everywhere. It doesn't change sign. Okay. Remember, according to this convention here. If it's convex, it's positive. It's concave, it's negative. Okay. Shear force. Okay. V of x can be computed as dm dx. Take a simple derivative. Okay. And we get W L minus x. Okay. And so if we were to display this on the graph, okay, 0 to L, right, you get something that looks like this. Linear function starts out at W times L, okay, which is exactly what you would expect, right? Because that's the force that opposes a distributed force of W times L, right? And it's plus, goes to 0, and it's plus because of the sort of the following convention that's been adopted. Okay. So there we go. Okay, this is how you solve Euler-Bernoulli beams. Okay. All right, and so now I think we're ready for the Euler or Bernoulli-Euler beam. Let's look at stiffness matrix. Okay. And the way we're going to set this up, right, is we'll take our beam and assume that it's pinned here. Okay. It means that it cannot go left and right, cannot go up and down in these locations. Okay. And so the only degrees of freedom that remain, okay, would be the slopes, okay, or the rotations that I'm going to call U1 and U2. So DOFs of interest, right, degrees of freedom, are the rotations or slopes at x equals to 0 and x equals to L. Okay? And what these slopes are going to do, they're going to go and deform the beam, right? And will create moments at these locations. Okay? So it will generate M1, right? And moments M2. Okay? So what we'll do, we'll proceed as in the case of a truss, okay, and apply rotations or slopes one by one. Okay. So let's take the first situation, right? This is our structural member. Okay, we'll abstract it as a line and some nodes. Okay. All right, we're going to set U1 to be 1. Okay. we're going to set u2 to be 0, right? And also our vertical displacements are 0, right? So v1 is 0, v2 is 0, okay? What's u? u1 is dv dx evaluated at x equals 0, and u2 is dv dx evaluated at x equals to L, okay? So rotations or slopes, as I said. Okay. So now let's solve our differential equation, right? So we're looking at EI, right? dv dx for 4 equals to 0. Okay, so there's no particular solution. Homogeneous solution is it, okay? V equals to VH equals C1 plus C2x plus C3x squared plus C4x cubed, okay? And the boundary conditions are V at 0 is 0, dv dx at 0 is 1, right? We're imposing a slope of 1. V at L is 0, and dv dx at L equals to 0, right? So we're only controlling 1 degree of freedom. Okay? So if you look at page 117, okay, you find that for this situation, v of x equals 2. V of x equals to x minus 2 over L x squared plus 1 over L squared x cubed. Okay? So you completely calculate the displacement, right, corresponding to this situation. From the displacement, you calculate the moment, right? Equals to EI d squared V dx squared, okay? So if you do the calculation, okay, you get EI minus 4 over L plus 6 over L squared x, okay? And so now you take the M, right, and you evaluate it at x equals to 0, right, and at x equals to L, okay? And what you find, right, is, well, your displacement looks like this, okay, which may be plotted as follows, right, comes out, satisfying the slope condition of 1, right, and then comes in with 0 slope like that, okay? You find the moment here equals to 4 EI over L, okay? And you find that the moment there equals 2 EI over L, okay? So you go and package it, right, into the first column of the stiffness matrix, 4 EI over L, 2 EI over L, like this, okay? Then you repeat for U1 equals 0, U2 equals 1, right? So what are you doing there? You solve the problem using the following boundary conditions. V of 0 equals 0, dv dx at 0 equals 0, v at L equals 0, dv dx at L equals to 1. Okay, so you go through the same procedure, right? You find that your displacement is now distributed as follows, right? Here's your slope of 1. Okay? And then the corresponding moments are K, so M equals to 4 EI over L, and the moment here is 2 EI over L, okay? And so you collect another column of the stiffness matrix, 2 EI over L, 4 EI over L, okay? And so you find that if you want to compute M1, M2, relating them to U1, U2, right, which are slopes, the entries of the matrix that relates the two quantities are 4 EI over L, 2 EI over L, 2 EI over L, 4 EI over L. Okay? And so what we do here, we arrive at the stiffness matrix for the Bernoulli Euler beam. Okay, we stop here.